Okay, good afternoon, everyone. Are you ready to learn some physics? I am sure you do. That's why you are here. Oh, I already see something is missing here. I forgot to upload. Back to the business. So here is this question. It says find the kinetic energy of a charged particle when it, let's say, reaches here, right? So it's asking for kinetic energy. So kinetic energy here can be found from the speed. And since this is a proton, we can find or look for the mass of proton. So mass and velocity. So half mass times velocity squared gonna give you the kinetic energy. So you know kinetic energy here. So there is potential. So that means you should be able to write potential energy. So that means you know kinetic and potential energy here. There is potential, so that means you should be able to find the potential over there, potential energy over there too. So only thing that's missing is kinetic energy, assuming that we remember conservation of energy, right? So conservation of energy tells us that total energy over here must be equal to total energy anywhere else, unless there is some external force acting. Here we are neglecting all other forces, but the electric force, and that comes from these potential, these plates over there, right? So that's what this is asking, okay? So did you folks made notebook LM and try learning something from there or not? So for example, as a practice, let's say I see this problem. Now I recognize this is problem related to conservation of energy. See, that we need to know it if we want to learn it, right? So what I did was I just, right before we started this class, this is what I was doing. How do I solve related to conservation of energy of a charge? So we have to be specific. Otherwise, remember in physics 1, we learn about conservation of energy as well. It's the same thing. But in that case, that would have some sort of, like let's say that would be just object moving in, let's say, where the height is changing, and because of the height change, the potential energy is changing, right? Speed changing means kinetic energy changing. Same idea here. But here, it's not the height that's changing the potential energy. Change in height changes gravitational potential energy. But this one is electric potential energy now we need to look at, because we're talking about motion of charged particle, and charge is affected by the potential or field. And remember, field, potential is just the two different ways of saying or let's say representing the same thing, okay? So sometimes we talk in terms of field, sometimes we talk in terms of let's say potential. It's like talking or solving problem using energy concept or force concept by drawing free body diagrams and so on. So in this case, potential being, let's say related to energy, we want to use conservation of energy. So I have a bit more sources than what I have provided for you. So what I get may be slightly different than what you will get even if you were to type the same thing. How do I solve problem related to conservation of energy of charge? So if you can quickly, let's say, get in the notebook LM, can open in the browser and get in the notebook LM. Can you go ahead and type the same thing in your in your notebook LM and see what you get? I got a lot of these things, but they are in steps, right? Many steps there and details. And it says, hey, you can use this conservation of energy principle after knowing that, right? So it guides you, you know, what needs to be done. And then finally solve for unknown quantity, right? And then it also says there is a key concepts there. Energy has a unit, sorry, potential has a unit, joule per coulomb, and so on. So I'm not going to read this everything, but there are these 5 main steps. So now I would like to refine this. Could you, let's say, make it brief? Make it brief. Let's say, including only main steps. Let's see what it does. Okay, I'm just doing this right now. Let's see what it does. So now it is basically made that long information, okay, and it made it shorter. Okay, so that's what you can see here. So identify the system and then choose the positions and determine the energies and apply the conservation of energy and solve for unknown. So now it has only those steps, okay, many steps, rather than including all the details. Okay. So identify the system here means, okay, energy of what, right? So in this case, what is moving? It's the proton. Okay. And then choose position. So now conservation of energy is saying that total final energy is equal to total initial energy. So we can identify where is initial position, where is final position, right? So we note that down. And then after we do that, what did it say? Determine the energies, right? So it's going to have kinetic energy, and kinetic energy is given by half mv square. And potential energy is product of charge times the potential, okay? And apply conservation of energy, and it even tells you what is the conservation of energy equation is. That is final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. So if there is some non-conservative force present, then you need to include that non-conservative over there. And that's going to give us change in kinetic energy plus change in potential energy is equal to the non-conservative force. So in this case, we don't have non-conservative force. We are saying, okay, this is electron is flying there, or proton in this case is flying. So it's not rubbing on any surface or anything like that. Maybe there is some air, so they're going to be dragged due to air. But we are saying, okay, let's ignore that because that information is not there. So it tells you, you know, how to go about solving any such problem. So now let's do that here. So in this case, object of interest is proton. A proton is moving. So mass of proton, oh, do I remember that? You guys want to verify this, okay? Since looks like I did not write mass of proton anywhere here, so I'm just pulling it out from my head, but sometimes things may get messed up, okay? So mass of proton and charge of proton, we know, is, let's say, charge of proton is same as charge of electron with positive sign, right? So it is 1.6 times 10 to the power negative 19 coulomb. Okay, so those information we know about the proton. And let's say this is the initial where it is entering. Maybe I should write that, right? And this is where final, that's where we are interested, what the kinetic energy is. We are asked to find what is kinetic energy over there. So that's going to be our final point, right? So that means the initial velocity is that is given for the kinetic energy, right? Initial velocity. So lowercase v, we're going to be using both v here, uppercase and lowercase. So make sure to differentiate them. Okay. So lowercase v is 3.0 times 10 to the power 5 meter per second. And then how about initial potential? Because we learned that potential energy, initial potential energy is equal to charge times the potential. So that means potential here is 0 volt. See, it's showing right here in the diagram. So if it is 0 here, it is 0 everywhere here, okay, on the plate. It's a conductor. Conductor has a constant potential. We learned that, right? And then how about, so what are we looking for? Yeah, we could have asked, let's say this problem could have asked, what is final speed here? Even to find final speed, what you need to do is just do the same thing. Find the kinetic energy, use the conservation of energy, and final speed is in the final kinetic energy. So in this case, we are asked to find kinetic energy when emerges through the hole in the positive plate over here. So we are looking for final kinetic energy over there. Okay, so that's what it is asking. So using conservation of energy, oh, we know one more thing here. BF, I forgot to write. Final potential is 250 volt. Okay, that's where it is reaching. So uppercase B for the notation, and also the same thing for the unit, okay? Using conservation of energy, let me, using conservation of energy, final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. So we are asked to find final kinetic energy, so we don't need to write this in terms of mass, okay? So I'll just keep it there and then move this one to the other side. Let's say Ki plus Ui and minus Uf. So these are not given as such, so we need to open these, okay? So that means we need to write them explicitly. So kinetic energy is half mass times velocity squared. That's the formula we have learned. But I am writing initial kinetic energy here, so that means I'm going to write I subscript in the speed. And then mass here, the object is proton, so mass of proton. So that's what I'm going to write. You don't have to. There is no another object, so you can just leave it as a M. But I'm trying to be more specific here, okay? And then plus, move to the initial potential energy, and we know it is given by Q times V. Just like we had a gravitational potential energy, mgy or mgh, Now, instead of that gravitational, we have electric potential. How do we find that? Q times V. Okay, so that's what we write. And in this case, Q is still charge of proton. And then this is initial potential energy. And we know the initial potential energy is 0 here. So that term gonna be 0. Now let's move to another one, which is that over here. So this is Q proton times VF. Okay. So what do you expect? Will it slow down or gonna move faster here? So what do you expect? Oh, I'm not finding the speed, so probably it's not going to be directly comparable. But if I was finding speed, and then, based on this setup, can we tell final speed we expect going to be smaller or larger than this one here, right? But here we are not calculating speed. So now it looks like we have everything we need, and this is 0. I like that very much. Okay. So that means this is half, and mass of proton is 9.8. Did anybody check? I think that is correct. Okay. That many kilogram. And then speed is 3.0. Let me not write the unit over here because I'm running out of space. 3.0 times 10 to the power 5. And this one has to be squared, so that means 3 gets squared, 10 to the power 5 gets squared. When we square that, it becomes 10 to the power 10. Okay. And then now, this is just this term over here. Now we move to this term here. So minus charge of proton means, so it's a positive, so I can just write this as a 10 to the power negative 19. Okay, so that's charge of proton. And the potential over there is 250 volts, right? So we need to simplify that, and the unit gonna be in joules. And this number gonna be small, very small. So when we have very small number, we may also write energy in terms of what's called electron volt. So once you have energy in joule, what you do, you just divide by, this charge of one electron, that's it. But here it's not asking us to find energy in a particular unit, so we can just leave it as a joule. But if you are asked to write in terms of electron volt, now you know what to do. Once you have calculated value in joules, you divide that by this number here, which is charge of an electron or proton. Okay? So looks like this is 10 to the power 5 and square is 10. So this is going to be 10 to the power negative 21 over here, the first term. So let me make some room, and yes, we need calculator. So I'll leave it for you to calculate, but let me simplify a little bit more. So half, I'm just copying, and then 9.1, I'm just copying that. And then see with this 3 here, see this is exponent, I'll write that later. So there is 3, and this 3 is being squared, so that's going to be 9 as well. 3 times 3 is 9. Now this exponent is 10 to the power negative 31. And this exponent is 10 to the power 5 squared, means 10 to the power 10. So that's a positive 10 exponent, and this is negative 31 exponent. So when we multiply that, we're going to get 10 to the power negative 21. Just subtract 10 from 31. They have opposite sign, means they get subtracted. Okay, so that's what happens. So that is first term. Second terms, looks like, I cannot simplify the exponent much over there. So I'll just leave it like that. 250 times 10 to the power negative 19. So it is easier if we were to make both of these exponents kind of similar. Okay. So for example, this is 21, this is 19. So we have two space, right? Like we need to, if I were to divide this by 100, then this is going to be 10 to the power. Oh, let's see. So not divide, but yeah, 10 to the power, let's say 2. When it goes up, it's going to be 10 to the power negative 21, but I cannot just divide. I need to also multiply. Okay. And so that means we have to multiply by 100, and it's going to be 10 to the power negative 21. Okay. But I think carefully use the calculator and come up with the number and divide that number by, so that's going to be in joule, okay? And divide that number by this 1.610 to the power negative 19 joule per electron volt. Then if you do that, then this is going to be in electron volt, okay? So here there is this hint. It simply says, okay, there is no another potential or field that's affecting the motion. So that means when it says, okay, when it comes out, that is like that's the final point, and that's not going to affect anything. That's what it is saying. Okay. So basically, we use this equation several times in physics 1. We are doing the same thing. Only difference is now we have just the ugly numbers. That's it. Okay. Everything else, basically the same thing. So we learn how to use kinematics, how to use Newton's law, and how to use dynamics. Sorry, the conservation of energy. So we used all those three main idea we learned in physics 1 over here. Okay, so we just use that borrowed idea here. Okay, so now let's talk a little bit about, potential and field. I said, okay, potential is a one way of describing the, let's say, same thing, basically, versus field is another way. Okay. One is vector quantity, field is a vector quantity, potential is a scalar quantity. So it's like using dynamics versus energy idea. Right. So that's what that is. So, for example, if we have just a charge, point charge, we know the field just comes out. So these red lines are field lines here. Okay. So from positive charge, the field lines are just radially out. Okay. And we also learned that the potential is same at equal distance because we know the potential of a point charge is given by kq over r. So circle or sphere in 3 dimension, that means it has same potential. So if we have a surface that has the same potential, so just like if we have charge inside is some spherical conductor like a ball, right? So let's suppose we have something like a soccer ball, but that is made up of metal, okay? And then what happens? If we have charge inside, there's going to be potential on the surface. Everywhere, it's going to be same. Because all these points are at equal distance, means at radius equal to the radius of that circle or sphere, depending on whether you are talking in terms of 2 dimension or 3 dimension, okay? So that's why these blue dash line that I am drawing, they are all at equal potential. They are called equipotential lines, okay? So what happens here? Potential is inversely related to distance. So that means here we have lower potential compared to over here, let's say higher, if we are just comparing these two. But if we compare these two, then this one has a higher potential than that. So if you, like let's say if it's easier for you, let's say I can give some numbers here, but these numbers not any way any realistic, actual number, but just giving an example. So if this is 200, oh, hold on, lower potential. It's supposed to be other way around. 150, then this is 200. So maybe it is just then we're going to have 250 over there. Okay, larger. Closer you go, higher going to be potential because smaller the r, larger going to be the potential for same charge, right? K is constant. So charge and K is constant for a given charge. So it simply depends on R. So closer you go, what's going to be the potential? Larger the potential. And of course, the electric field is also larger, closer to this charge. We know that. And now, here, what do we see is these electric field lines is crossing these equipotential surface. They make 90 degree. Okay. So they are always perpendicular. So that means the field is perpendicular to the equipotential surface. And since field and force, depending on what kind of charge we're talking about, either going to be this way or that way, force this or that. If it is negative charge, force is going to be pointing this way. If it is positive charge, force is going to be pointing that way, right? But either way, it is still perpendicular. Force and field are perpendicular to the equipotential surface, always, okay? And how are they related then? So we're going to write this equation, a little later as well. Actually, we're going to derive. But what happens is the change in potential over that change in position. gives us field. So when something is changing with respect to position, we may also call gradient, okay? Gradient. So here, potential is changing with respect to position. So we may also say, okay, this is potential gradient. So field is a potential gradient, okay? So there is one negative sign that simply means that it points towards the decreasing potential. Field line points towards the decreasing potential. So field line goes from higher potential to lower potential. So for example, in our previous problem here, if we were to draw field lines, the field line between these two plates would be pointing this way. Okay, field line goes from higher potential to lower potential always. That's what it's going to look like. So this charge is moving in the opposite to the field, and this positive charge is moving opposite to the field. It likes to move along the field, but when it has to move opposite to the field, it's going to slow down. So that's why this final kinetic energy, or I should say, if I were to calculate speed over here, would be smaller than over here. So whatever kinetic energy it has over there, so kinetic energy over here going to be smaller. It's going to be coming out with smaller speed. So basically, this equation is basically telling us same thing as well. So field line is going in the decreasing potential direction. So see here, higher potentials near the charge, and field line is going from higher region to the lower potential region, right? So basically, that's what that negative sign means. So field being a vector, this simply means direction. Negative sign simply gives direction because field is a vector quantity. So value of the field, when we are just interested in value of the field, we may just write delta V over delta X. But if we need direction, this negative sign helps us to tell which way the field line going to be pointing in the equipotential region, okay? So for example, I have this another one here. So potential is always higher at the positive charge. How do I know that? Because V is given by KQ over R. So when charge is positive, this potential is positive. Here, this charge is negative. See, this charge is negative here, where I'm, how I have drawn it. So this is negative. So if I write negative, you may get confused, hopefully not. Okay, so this negative is coming from this charge being negative. So negative numbers gonna be always smaller than positive number for the scalar quantity. So that's why the potential is higher here. Okay, so that's why you see the field lines going something like that. And even if we, and we know the field line always goes from the positive side to the negative side. We have learned that, okay? And then now these fields are uniform. We learned that these fields between two charge plate, they are constant. We learned that in last class. So that's why their, separation is like this. They are straight line, separation distance between them everywhere is same. So that is uniform electric field. And we learned that the potential is perpendicular to the field line. So that's why this dash line here, dash blue line, that is potential. And these lines are perpendicular to the field. Okay, so that's how field and potentials are related in terms of direction and in terms of equation. I just wrote this equation over here. Okay, so that's how they work out. So now I talked a lot. So here is your turn. So go ahead. What do you think? So I'm going to open the poll. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So it looks like staircases and mostly C. Let's see what C has here. Work done is 0 because the force is perpendicular to the displacement along an equipotential line. Yeah, that sounds correct. So if field is going something like that, equipotential is that, right? Equipotential. So field and force, they are in same direction. So force gonna be this way and displacement gonna be this way. Let's say if we are moving along the equipotential. So the angle between them is 90-degree, means work done being the force times displacement times cosine of angle between them. What happens? Cosine 90 is 0, so that's why this is 0. Okay, so that was the field and the equipotential. So now I'm going to move to another section where we talk in detail about the capacitors. Although we already talked about capacitors, basically, we've been saying, okay, there is one plate, there is another plate, and we can put charge on them, right? So when there are two metal plates separated by a certain distance, and in between the plates, either let's say there is air or some sort of insulator, and then we call that capacitors. So in a circuit board, this is how the capacitors looks like. See these cylindrical ones, right? These are resistors. We haven't talked about this. This is going to be on the another class, okay? So these are resistors in the circuit. This is capacitor, this is capacitor, this is capacitor. And it's kind of hard to see. There is this thing. This is also capacitor, okay? So this capacitor has value in the order of microfarad, okay? These tiny ones, you see, kind of hard to see. They have capacitor in the order of picofarad. Pico means 10 to the power negative 12 farad, okay? So anyway, so if I were to open either this kind of capacitor or this kind of capacitor, okay? either this small picofarad kind of capacitor or this big microfarad kind of capacitor. What do I get? What do I see inside? There are going to be two metal plates. Okay. See here how there is this insulator here, and there is metal plate. You see there? So there is metal plate on both sides, and there is insulator in between. This insulator has fancy name. We'll talk about that later. It's also called dielectric. Okay. But we can have just air. And this is how the symbol of capacitor look like. You draw two parallel lines. Okay. How do you draw a cell or a battery? A longer line and shorter line. So that is cell or battery. This one, capacitor. What's the difference? Capacitors, we draw two equal length line. Cell or battery, one is shorter, another one is longer. Longer, we call that positive terminal. Shorter, we call that negative terminal. Okay. So capacitor also, when we charge it, what happens? One plate becomes positively charged, another plate becomes negatively charged, like a battery. Battery has pole. One side of battery is positive, another side of battery is negative. So if you have to use two batteries, and if you don't put them in a certain order, it's not going to work because it has poles, and we have to put them in a certain way. And we'll talk a little bit more about battery in the coming classes. Here we are focusing on capacitor. Okay. So we can charge a capacitor, means we can store charge. Whenever there is charge stored, what it means is we can also store energy. Okay. So since charges are separated, we can say, okay, there is field between them. We can say there is potential difference between them, right? We can say potential difference between them. Let's write the equation of potential difference in terms of change in potential energy. So if you are wondering where did this equation come from, this is the definition. That's how we define potential. B is potential energy over Q. So if we are talking about difference, it makes sense to write in terms of difference, okay? And potential energy could be electric potential energy, gravitational potential energy, and so on. So that's why, to make sure that we're talking about electric potential, there is this E subscript, okay? So basically, this is definition of potential. So now potential energy we learn is, when potential field does work, basically it either takes out the energy from the system or puts energy in the system. So we can write that in terms of work done. Okay. So work done is force times displacement times cosine of angle between them. Okay. So force here being electric force on a charge, we can write that as a Q times E. So that's why this is like a force. Okay. And delta x is a displacement. So think about moving a charge over here this way or that way. Okay. So the angle going to be either 0 degree or 180 degree. Cosine 0 is 1. Cosine 180 is -1. Okay. So that energy going to be either positive or negative. So here, let's say the charge is just moving in the direction of field. For example, if I let positive charge move here, it's going to move this way. So displacement and field going to be in the same direction. So I can write something like that. Okay. So now this Q cancels with this Q, and this delta X, see, basically the equation we wrote in previous slide, delta V over delta X is E. Basically, that's what we are writing here. Over there, we included the direction of field as well by putting negative sign. But when we don't put negative sign, we are not including the direction. We are just writing the value. That's all it means. So here we are just writing the value, not the direction of electric field, because direction of electric field is visible right there. We can tell it goes from positive to negative. So I'm not writing that. Okay. So basically, that's what the equation we got, and that's the equation we had written in the previous slide. And remember, I said, okay, we're going to derive that. So this is the derivation of that equation. But here we like to write it this way. Okay. So here delta X. So for example, if we let some charge to move through from one plate to another plate, how far it moves? Equal to the separation distance of the plate. So separation distance between the plates is denoted by this lowercase d, and that's what I'm writing. So I'm replacing displacement by delta X is general notation for displacement we used and learned in physics 1, right? And that's what I'm doing. But for this special case, that delta X is going to be same as a d. Okay, the value of delta X is going to be same as d. Okay, so that's how I'm writing. Okay, so that is the relationship between potential difference and electric field inside a capacitor. So if we recall from a class, I think it was second class, when we talked about charges and field on the plate like this, we said electric field in this kind of configuration can be written something like this. Okay. And this Q over A can also be written in terms of surface charge density. Oh, looks like I did not write that. So it could be also written as this is the field. And in this case, we are just multiplying field by D. Okay, that's another way to write it. So here what I did was I rearranged this equation. See, we have delta V over here. So I solved this or rearranged this for Q. So when I do that, what happens? These gonna go multiply that, and this D gonna come and divide. And that's what it is doing. These two are multiplying delta V, and D is dividing delta V. Excuse me. Remember that when we write like this also means delta V divided by 1. That's the same thing, right? So now this allows us to write, see what we have here. This is a constant, electric permittivity of free space. So that means if there is nothing in between two plates of capacitor, but simply air, then we have this thing there. It's a constant. And A is the area of the plate of the capacitor. Okay. So for example, let's say you open the capacitor and you found this big plate. Then the area is this area of this plate here. Okay. And D is the separation distance between these plates. See how they are rolled very closely? What happens? Separation distance is in millimeters. They are small, okay, in a capacitor. Those plates are very close. So all these are constant for a capacitor. If you build a capacitor, what happens? You have fixed plate. It has a fixed area, and the separation distance between them is already fixed. So that means all these three things are fixed, and those are constant in another word. So those three constants are, denoted by a single constant. And since it came from the capacitor, we say, okay, that's the capacitance of a capacitor. Okay. It is called See, capacitor is a device. Capacitance is its capacity. Okay. So capacitance is capacity, and capacitor is device. Okay. The name of this device is capacitor, and capacitance is the capacity of that capacitor. So what do we see? The capacitance depends on area of the capacitor. Larger the area, larger the capacitor. What that means? See, capacitor is charge storing device. So when we say it has larger capacity, that means it can store more charge. It's like our, let's say, trash can. If trash can is bigger, then we can store more trash. Okay. So same idea here. Larger the capacity, larger the amount of charge we can store. Okay. And how do we make capacitor larger? Make area larger, make separation distance between them is smaller. See how D is in the denominator? So capacitance is inversely related to distance, directly related to area, and this quantity. So when you have material like this, dielectric, then this thing changes a little bit. Okay, we'll talk about that separately. So that is called capacitance of a capacitor. Okay. So it simply depends on the geometry. Okay. What is capacitance? Capacitance does not depend on potential difference or charge. Capacitance does not depend on potential or charge. It simply depends on its geometry, how it is built. Okay. So that's what this is. So now here is a question for you. So see how this area of this plate is. And here, although in the drawing it may not seem like a square, here it is a square. So that means this side length and this side length, they are same. See, I'm denoting them by L, L, the same. So now it says if we double L on both of them, so like you made something like that. Oh, to double both sides, we have to make it go like that. Ooh, doubled. Ooh, yep. And half D, by what factor have we changed the capacitance, right? So capacitance depends something like this. For your convenience, I have written that equation right there. So I'm going to open the poll. So what do you think? Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see how did we do here. Oh, again, another staircase. Okay. So we are changing both of these, right? A is changing. So when you double the length, what happens to the area? In a square, area is length square. When you double length, the area becomes 4L square, means it is 4 times of original. And from geometry, you can see here, see how I drew it? So now it's like a 1, 2, 3, 4, 4 of such area, right? My drawing is not perfect, but tentatively you can tell that, okay? So there are 4 there. So that's what it means, 4 times of the original area. So area becomes 4 times. So that means new capacitance, let's say C new, gonna be what? See, this is not changing because we're not inserting anything in between. So epsilon naught remains same, but the area is now 4 times of old area, and distance is half. So you move the plate closer. Closer the plate, larger the capacitance. So this 2 becomes denominator of denominator. So that means it's gonna go in the numerator and multiply 4. So yes, looks like it's gonna be up by 8. Okay. So if you forget about D, then that would be 4 up by 4, but we cannot forget about D. Okay. Anything you like to add or ask on this one here? Oh, it's 3 o'clock. Looks like a very good time to take a break. So let's take a break, and I'm gonna pull on this one after the break and gonna move to energy inside a capacitor. Okay, I'll see you in 5 minutes. Hey folks, so welcome back. So I'm going to open this poll. So let's go ahead and poll on this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly D, that is correct. So all of these are true for a capacitor. Okay, so it stores charge, it also stores energy, and basically it's the construction. Okay, great. So moving on. So you see here how when we throw a ball up, the gravitational potential energy of the ball increases. Similarly, when we connect a capacitor to a battery, and this is just a meter that measures the voltage or current. In this case, it's measuring the voltage. And you see the voltage here, this number, I don't know how clearly visible to you. It says 12 volt, which is the voltage of a battery like this. Often we find this in car, okay? To start a car, we use this kind of battery, okay? So if your car starts, it stops starting, then you have to change this kind of battery, okay? So in this case, what is battery doing? Just like you are using your stored energy, the energy you got from your food, and pushing this ball up. So in that process, you are losing your energy, but you are giving that energy to the ball so that ball goes higher. When ball is higher, we say, okay, it has higher potential energy. Similarly, the battery separates the charge. Okay, so makes one plate positively charged, another plate negatively charged by separating. For example, let's say right now there are positive and negative charges. So we separate them like that. Okay, so that's what happens. So one plate becomes positively charged, another plate becomes negatively charged in this case. So here it says ground here, black terminal, there is red terminal. So you see here it's written positive here. So that plate, out of those two rolled plate, the one that is connected to this terminal becomes positively charged and this terminal becomes negatively charged. Okay, so in this capacitor. If you were to remove battery now, what happens? This capacitor slowly loses charge. If you remove battery and connect with a wire, then it's going to quickly lose that charge because the negative charges from this terminal going to come here and combine with the positive charge, and this becomes what we call discharged. So right now we said, okay, it was fully discharged, and when we connected to a battery, what happened? This charged the capacitor plate. So capacitor plate became fully charged, okay? So it has charge separated means now it has energy, right? Electric energy. It has electric field. It has electric energy. It can apply force on charged particle. So basically, a different way of saying it is now it has charge, or it is basically it has now energy. And that energy is given by this equation here. Remember, potential energy we learned is charge times change in potential, right? So this came from the definition of potential energy. So in this case, when this is, there is no charge, the energy going to be zero, right? And when it is fully charged, energy seems to be like Q times delta B. So on average, between no charge and charge, so we say, okay, energy in a capacitor is average of those two. Yes, so we have to do it properly, we have to use calculus, but we are just, I'm making some hand waving argument to justify this half, okay? So charge, it goes from zero energy when there is no charge to maximum energy, which is Q times delta B. So on average, it has this, average of 0 and Q times delta B. So average is like that. So this is the definition. So half of Q times potential difference. Half of the amount of charge in one plate times the potential difference between the plate. Okay, so if we're talking about car battery, then the potential difference between these two plates on this capacitor charged using a battery, we have voltage 12 volt. Okay, so delta B would be that much. How much charge? I don't know. It depends on the capacitor of the capacity of the capacitor. So we can write energy in terms of capacitance as well. Okay, so for that we can use the formula we just learned in the previous slide. Q is C times delta B, right? So I can replace this Q over here by C times delta B. So when I do that, what's going to happen? Oops, it's going to be this, okay? Now, if we do not want to use, let's say a potential difference at all, then you can replace potential difference by Q over C using the same equation, right? So if you were to replace this delta B by Q over C, then you get this, because Q is already there and another Q comes in here, C there. So Q is squared over C, and 2 is already there in denominator. So that's going to be there as well. So there are 3 different ways you can write the energy stored in a capacitor. Depending on what you want or what is known, you can use either this formula, or this formula. Okay. Okay, so that is energy in a capacitor. So now, say this millijoule, like a millimeter. So 2 millijoule means 2 times 0 times 10 to the power negative 3 joules. Okay. So there are 1,000 millijoules in a joule. So when we convert millijoule to a joule, we need to divide by 1,000, which is also same as that. Oh, I'm just noticing there was a direct message few minutes ago. So when you write this kind of message, try to write to everyone so that people can see it. So the electrons in a battery will move to the capacitor. Excuse me. That question was very powerful, looks like. That give me sneeze. Okay, so yes, there are extra negative charges. Negative, that means those electrons from negative charge, electrons from negative terminal of battery. So electrons from negative terminal goes to this and becomes negatively charged. At the same time, so what happens is electrons from this plate gonna move to the positive terminal of the battery and leaving this one positively charged. So electron goes there, electrons leaves from another plate. So from one to the one plate, electron goes to a one plate, and electron leaves the another plate. That's what's happening when we are charging a capacitor. Okay. Okay, so back to this question here. So volt. So the answer is in millijoules. So even if you don't convert it, you should be fine. And you may not have to insert the number. Looks like you are doubling the potential to the same capacitor. You are doubling the potential to the same capacitor. What happens to the energy? Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, now let's see what we got here. So it majority for C, but there is B as well and E as well. So is it 4 times more or 2 times more, right? Okay. So now what's happening here? Potential goes from half volt to 3 volt. So change in voltage is doubling, 2 times of original. New delta V is 2 times of the old. Okay. So that means what's gonna happen to the energy? That's what the question is, okay? So there are 3 equations that we can use to find energy, but which one is suitable in this case? So this one has a potential difference, great, but there is also charge. We don't know anything about charge here, okay? What happened to charge? And when we increase potential, the charge usually increases because Q is C times delta V. So not constant. It changes with potential. So when you are changing potential, charge is also changing. So you cannot tell just by using this equation. So this is not a good equation to use, okay? Same thing goes with this because there is that, and there is not even potential. So we need to use this one. See, the C is always constant. So now it says, okay, how the energy changes with the potential. It gives us that, okay? So there is nothing other changing when we are changing the potential. So that means this equation is suitable to use in this context, in this problem. Okay. So now what happened? Delta V becomes 2 times delta V. So B square is in the equation. Delta V square means it has to be square. So it has to be 4 times delta V square. So because of this delta V doubling, what happens? Energy becomes 4 times larger. See, there is 4. So originally there is 2 millijoule for 1.5. Then doubling is going to be 4 times of that one. Means that's going to be 8 millijoules, not 4. Doubling voltage increases energy by 4 times because this is how that is related. So if you are thinking, okay, why cannot I just say, okay, doubling voltage doubles energy? I already said, why cannot you? Because Q is also changing, see? Doubling voltage, Q doubles. So if you were to use this, then this Q doubles, delta V doubles means they're going to be 2 times 2 means 4 times more. Energy going to be 4 times more. Okay. Or you can do something like this. Delta V 1.5 volts and energy, let's write energy is 2 millijoule. So since answer is given in millijoule, I'll just leave that millijoule. And delta V new is 3 volts, right? So U new is what? So for that, just like I said, you want to use this equation. So delta U new is half times C times this delta V new square means 3.0 square. And delta U old is half times C. C is not changing. It's the same capacitor. Okay. If the capacitor is charged, means we did not switch the capacitor. It's the same capacitor. It's 1.5 squared. So now to find delta U new, you divide that by old energy. Then what's going to happen here? You divide this by this. So half C cancels, giving you 3 square, 3.0 square divided by 1.5 square. So this ratio is going to be 4 times larger. Okay. So that's why delta U new is 4 times this delta U, which is 2 millijoule. So that gives you 8 millijoule. So this is systematic way of doing it, but we don't have to do that to answer this question. We can tell, okay, this is delta V squared dependent. So when we double, square becomes 4 times, means energy becomes 4 times. Easy peasy that way. Okay. So looks like the answer is D. Did I choose the answer? Oh, not D, E. So that's that. Okay. So it looks like we always make mistake when we are doubling something where that thing is being squared. So let's not keep making the same mistake again and again. Okay, so here is another drawing of this capacitor. So 12-volt car battery is hooked up to a capacitor with a plate of area that much a distance. So now it has all the details, okay? How much charge builds up on a plate, okay? So here what we have is delta V. Delta V is 12 volt, potential difference between two plates. And the area is 0.1 square meter. Hey, directly area is given. Sometimes you may be just given length. Or if it is spherical capacitor, you may be given just radius. So in that case, area would be pi r square. Okay. So for this kind of situation, area would be L square. But here, area itself is given, so we don't have to worry about that. And here, the separation distance is 8.85 millimeter. So here, the area is in square meter. So that means we need to convert this millimeter into meters. So millimeter to meter, we need to divide by 1,000. And in terms of exponent, we can write something like this, 10 to the power negative 3 meters, okay? So Q is what? Okay, so what did we learn is that Q is C times delta V. So delta V is given, need C. And we learned that C depends on geometry of capacitor, and geometry is given. Epsilon naught A over D is C, and then that is delta V. Okay. So now this epsilon naught is a constant. We can find that, and let's see if I remember that. K is -9, but this is -12, I think. And then area is 0.1 meter squared. And then there is delta V, which is 12. And divide that by D, which is 8.85 times 10 to the power negative 3. Okay, this one has to be squared. Oh, see, I'm clever. I put this number 8.85 so that it cancels, okay? Okay, so there is 12. This 10 to the power negative 3. When it goes to the numerator, it becomes positive 3. And there is negative 2, means they're going to be a positive 1 when we combine these two. And then this is 0.1 square, means it is basically 0.01. 0.01 times 10 times 12. Oh, so $120, and then that 120, so 1.2 coulomb. Looks like a lot of charge there. The 0.1 square meter is also large area. I think that helps. Okay. So you want to double check this. Coulomb is unit of charge. Okay, so that is just part A. There is part B. It blocks that. Hopefully you already got that. How much energy is stored in the capacitor now? Okay, so U is what? So in this case, we have even Q, we have delta B. So we can use actually any one of those three equations we had here. Okay, we can use any one of those because we just calculated Q and we have delta B. So you can use that or use that Q square. Oh, we need to calculate C for that or use this. And basically, we already calculated, C was, what was C here? So this is basically a C. So I think since we found the Q, it is a good idea to just use that Q times delta B, half Q times delta B. That way we don't have to do the calculation of C again. Okay, so Q from here and delta B is 12. Was that 1.2 and 12? And this is going to be in joule. Okay. Six, 7.2 joules. Check numbers with your calculator. Don't believe in the numbers that I do in my head. Okay, so now let's talk a little bit about dielectric. So how the capacitance. So here this equation is the capacitance of a capacitor when there is just air inside the capacitor, right? So now if we insert some insulator, and insulator, fancy name for insulator is dielectric, and often it is just paper, cardboard you saw inside that, in that picture I showed you, okay? So that's what happens. So you put insulator. So here there is no insulator or dielectric. Now there is dielectric or insulator. So here the field was going from positive to negative, nice, without any interruption, okay? So when you put insulator in an electric field, what happens is the insulator gets polarized. The charges just align themselves. Positive charge aligns themselves in the direction of field, and negative charge is going to align slightly opposite to the field. So here, field is going from left to right. So that means this here is the positive and negative charge that develops on the insulator, okay? So insulator is just this cardboard here, let's say, paper. And now this is the polarization of charge, okay? So when you put insulator in a field, what happens? Some of those charges line up themselves. In a small pocket, they line up themselves with the field, in the direction of field or the opposite, depending on their nature, or positive charge lines up with the field in the direction of field, but negative goes opposite. So because of that, they develop their own tiny, tiny, tiny field. Okay. Excuse me. I am denoting that by E with the D subscript, means field due to dielectric. These blue lines you see, that's what they are. So they are all over places. They are tiny, they are not large as that I am showing here. If I make it tiny, then it's not going to be visible, okay? So because of that, it's made a bit larger. That's what happens. So what happens is now field becomes smaller. Why? See, the original field was this much large. Now there is another field pointing in the opposite direction. So if this is 10 and let's say this is -1, then the total going to be +9, smaller than the original 10. Okay, so this polarization decreases the field. And we know in a capacitor, field and potential difference, they are directly related. We wrote that equation. E times D is potential difference. So field is smaller means delta V also is smaller. So delta V decreases when you insert, okay? So now, let's say you fully charge with 12 volt here, okay? Let's say you had charged fully with 12 volt. Now you inserted this insulator. Then what happens? Potential difference here decreases. So 10 volt, 12 volt, these are just random number. But what I'm saying is decreases. That's what this equation tells us. Field decreases means potential difference also decreases. D we haven't changed, right? D is separation distance between them, which hasn't changed. So field change means the potential difference changed. So what that means? Now it has more room for the charge to get to that 12 volt. Okay, so we can transfer more charge. So before the charges were, when you have a lot of charge, they were about to jump and neutralize itself through the air. But now we put this barrier as the insulator. Because of that, the interaction becomes less, means you can crowd the capacitor or fill the capacitor with larger number of charge. So charge increases. So now you can put more charge for the same voltage. Same 12 volt, when you put same 12 volt with or without, what happens? Now you have more charge because of the increase in potential difference. So that means as if now the capacitor has a new capacity, more capacity. We call that capacitance increased, okay? So when we insert dielectric, what happens? Capacity of the capacitor increased. In case of garbage can, it's like saying, okay, it was about to full and you put some cardboard around, tall cardboards. Now you can put more garbage. So capacity of your garbage can increased. Same idea here, okay? By putting this insulator, the capacitance increases, or the capacity of this capacitor increases, okay? So I think whatever I said, I'm just writing those things here, okay? So here delta V decreased from 12 to, let's say, 10. That means C increased in this equation, according to this equation. So the factor by which the capacitance increases is called dielectric constant. Let's say here the capacity was 10, now it became 12. Increased by what factor? Increased by factor of 1.2. So this original, see, the voltage was this, now it became this. So by how much it changed? What factor? So it's 1.2. So dielectric constant in that case is 1.2 in this particular example, when the voltage goes from 10 to 12. If the voltage were to go from 10 to 20, for example, then it increased by a factor of 2, means this dielectric constant would be 2, okay? And this is not K. It is Greek symbol called kappa. Okay, so that's how the dielectric changes the capacity of a capacitor. Just like you can increase capacity of your garbage can by inserting tall cardboards around it and put more garbage. Similarly, you can put insulator in between the plates, and now you have bigger. So yes. So capacitance with the dielectric is that kappa times without dielectric. Sometimes these two may be combined, kappa and epsilon naught, and it may be simply written as epsilon, okay? But I'm not doing that. Okay, so here it says, okay, a parallel capacitor is charged using 100-volt battery, then the battery is removed. If a dielectric slab is slid between the plate, filling the space inside, the capacitor voltage drops to 30 volt. What is the dielectric constant of the dielectric? Okay, and we define that as the, like ratio of the change, right? Or let's say you can say, okay, Q is C times V. See, you remove the battery, that means you did not change the you are not changing the uh, charge, because only battery can supply the charge. Or you can also write this in terms of kappa. Oh, how do I write kappa? Kappa times C times new voltage. Okay. So if I use that, what happens? Kappa is now, see, the C cancels, and we can say, okay, it is like a V over V1, where V is 100 volt and V1 is 30 volt. So just like I said, when it goes from 10 to 20, what happened? Kappa is 2. Here it went from 30 to 100, means kappa is 100 divided by 30. Oh, yes. So that gives us 3.3. Okay. Okay, now let's look at slightly more complicated problem here. A capacitor can be made from two sheets of aluminum foil separated by a sheet of waxed paper. If the sheets of aluminum are 0.3 meter by 0.4 meter, so that means length is, let's say, 0.4 meter, and width is 0.3 meters. And separation distance gonna be same as the thickness of the paper, right? So I can write that as a 0.030, okay? A millimeter. So these are in meters, so it's a good idea to convert this into meters. So when I divide this by 1,000, it becomes 0.00030 meters. Maybe it's a good idea to write in terms of exponent here. 1, 2, 3, 4. Did I put enough? So I'm dividing by 1,000. So it should go, I think, 4 places. So 10 to the power, this is already 2, and 3 would be minus 5, I think, meters, okay? And in this case, the dielectric constant, kappa, is 2.5. what is the capacitance of the capacitor? Okay. So we learned that when we have, capacitance of new capacitor gonna be kappa times capacitance of the old capacitor. Here there is no voltage or charge given, just the geometry. So that's why I'm writing purely in terms of geometry here. So it's going to be 2.5 times epsilon naught times A over D. So this is the capacitance without paper. And now with paper, we have this one increased, right? So you can plug in numbers and get the answer. So this is for this permittivity of free space and times area. So for that, we need to multiply width and length. Okay, that divided by this tiny number. Four times 3 is 12. Times 2 is 24. And 6 is 30. So that 30, one of those cancels, and this becomes positive 5. So, oh, answer is right there. There. Okay, folks, so we learn about a device that can store charge, and its capacity can change whether we put some sort of insulator in between the plates or not. And if it does, by how much, we learn how to calculate those. We learn how to find the energy inside that capacitor. And before that, we also talked about the relationship between electric field and electric potential difference. Okay. So this concludes the potential chapter. So next class, we're going to move to the current, which is flow of charge. When charge is rushing and we're taking account of that, we say, okay, there is current flowing in the wire. What that means? Simply charge is flowing, okay? So we'll talk about that in next class. So I'll just leave it here. If you have a question, feel free to ask, or else I'll see you next class.
I have a quick question about the oh, sorry. Okay, I have a quick question about this last one.